Welcome to AVIAN's official systems engineering podcast. Today I have Rhett, Rich, Jim, and Keith with me to talk about model-based systems engineering. So on the first podcast episode, we talked about systems engineering. Now we're going a little bit deeper, talking about model-based systems engineering, which we'll get into a little bit. But in my mind, I imagine that's a little bit more of a specific topic than what we talked about on that first episode. So before we jump too much further into it, Rhett and Jim, if you want to go ahead and just introduce yourselves really quickly, that would be great. Whoever would like to go first.
I'm Jim Carroll. I'm Jim Carroll. I am a senior system engineer here at AVIAN. I support a program at NAVAIR, a new Marine Corps helicopter program that's just kind of getting started, and their program is fully immersed in model-based systems engineering, fully implementing model-based systems engineering. Prior to this, I have 35 years with NAVAIR in various roles, systems engineering and test and evaluation. So,
my name is Rhett Zimmer. I'm professional model-based systems engineer working at AVIAN and supporting the Navy. Graduated about 4 years ago with a bachelor's degree in systems engineering and operations research. I'm just about to get my master's degree in systems engineering. Since that time, I've been working into support SET at NAVAIR, so systems engineering transformation, doing model-based systems engineering tool studies, acquisition system reference model development, and I've also been in support of PMA 276 in the H1 upgrade, and as lead architect of AURA attack utility replacement aircraft.
Awesome. Where are you getting your master's from, Rhett?
George Mason University.
Awesome. Cool. All right. So let's jump into this topic. And let's start with that broad question. What is MBSE? I guess the other part of that is, how is it different? And actually, we'll say that for the second one. Let's start with just what is MBSE?
Yeah, so I'll take a first shot at it for you in a more general sense. And I'm hoping that the rest of the team here can fill in behind me, because I'm sure I'll miss some key details. But I came to this because I see model-based systems engineering as a dramatic change to the practice of systems engineering as an engineering discipline. Traditionally, systems engineering has been accomplished with the development of paper documents. And these documents would typically define requirements for the system that you're trying to develop. And we would build the evolution of the requirements and monitor the progress through that with paper. And everything would happen in the documentation. We would get working with our original equipment manufacturer, the prime contractor, develop the requirements set. And as the requirements evolve, those requirements would be translated into an actual weapon system. But our progress through that process is tracked on documents. Model-based systems engineering endeavors to replace the paper documents with a system model that describes what you're doing. The trouble with all the paper documents is that on a complex weapon system, it gets very complicated very fast. And it's very difficult to keep up. As a systems engineer, I spend as much time running around trying to keep track of the paper, and do I have the right versions? And is everybody working from the correct song sheet, if you will, for where we are today? So the idea of model-based systems engineering is to develop a model based on the requirements set that you have, and a model of the system that you're trying to develop. And by doing that, you have a centralized model that everybody can work on collaboratively. So everybody on the team has a single place of reference, if you will, to go and get information about what you're doing. And it's always the up-to-date set of information. So it becomes a collaborative tool for everybody to work from at the same time, and you make great progress. And it automatically does things like connect what your requirements are to the verification and validation requirements that you have, and so on. So to me, it's the advancement of specific engineering tools for systems engineers that we haven't had in the past. physics-based engineers and other competency engineers have had tools for a long time. Aero guys have had tools to predict aero performance. Structures guys have had finite element analysis that's done with computers to model structure, but we never had a way to model the system performance and the system requirements before. And MBSE brings that to the table for us.
Anyone else want to jump in?
Just to kind of add on to what Rich said, when we talk about documents, documents are really a representation of information, and they're only as good as when they are produced. But the information is constantly changing as the systems engineering process is going. So what a model does is allow people to work with the information and not the representation of the information through a set of documents.
Gotcha.
So that's one of the powerful aspects of model-based systems engineering.
So one question that pops in my mind, it sounds like this, and maybe it's abundantly clear, but I just want to be clear. Is all of this information now being digitized? So before it sounds like it was a physical representation, now it's a digital representation. Is that accurate or no?
Yeah,
Well, in reference to that, in the past, all of our documents that we've had in the past were all digitized. I mean, we took it off of a integrated a server, right? But there was no linkage of all those documents as related to time or abstraction of the level of maturity of the design, right? So what we've done is we've taken all these documents and distilled them down into 4 areas of structure, behavior, requirements, and parametrics that allows us to have use principles of concordance that allows us to look at that information at different views based upon whether or not that view happens to be from a structures end of it or an operational end of it, of that design. So, the level of abstraction is an important piece of the model-based approach, which I'm sure Rhett's going to kind of give us a little bit more technical detail on how that actually works.
Gotcha.
I would add that it's more than just digitizing a paper document. We have performance specifications today that describe our requirement set. It's not just a matter of making that an electronic document that I can read on a computer. What it does is it takes those requirements and puts them into a relational database, and you get the interaction of the requirements with each other and along those 4 pillars that Keith referred to, and get a better understanding of how not only do they work together, but how they relate to each other and how they can change and what the performance of your system will be as you manipulate those requirements.
Yeah, that definitely makes sense. Any last answers for that question before we move on?
I think I'd like to expound a little bit on what Rich just said just now.
Sure.
The relational database is a very important piece of this. Instead of a paper document where you're trying to describe the system in some way, you're making an abstraction or representation of that system in model-based systems engineering. You say this block is my system, and then you can apply functions to it, requirements to it, behaviors, state machines, etc. So different views of that system. So instead of an overarching description that's in a document and it refers to parts of it, you're representing that system and all the things that interact with it. And just like Rich said, as it's in a relational database, you're not limited to referencing other things via like words and so on. You draw a relation to that, and because of that relation, you can draw conclusions or analyses upon that relationship or sets of relationships.
Right.
So it really expands on the power and available not only in the configuration management piece, which has been mentioned before, but in the ability to draw conclusions and analyses on that data.
So it sounds like this, again, correct me if I'm wrong, but it sounds like this might make some of the testing a little bit easier. Was there a testing capability? So it sounds like you can set up like a scenario and then analyze it and figure out if something works or won't work. Is that what I'm understanding? And was there that capability, if I'm right, was there that capability before model-based systems engineering?
Well, there was, but it was kind of hard to abstract it from the information. When we work on our requirements documents, not only do we provide a requirement, but how would you test or validate that requirement? And as you go along through your design, the design starts to decompose ways of how I'm going to validate that design and then verify that that design met the operational requirement of the user. I think what we want to make sure that everybody understands is that model-based systems engineering isn't new systems engineering. It's the same system engineering that we've been doing for decades, is that we're using a new tool that allows us to do that. In the past, we used tools like DODAF, which came up with viewpoints associated with operational or systems or technical views that describe the requirements and the design, right? So those same views, whether or not it's an OV1 or a use case diagram, flows right into model-based systems engineering as well. So we teach systems engineering boot camp, through AVIAN for the Department of the Navy. And we add the structure of MBSE as a tool that encompasses all the systems engineering processes, technical and management processes. It makes it more efficient.
Gotcha.
And I would add, just as you wanted to know about the relationship of testing and the document-based approach. We did have that.
Okay.
And the attempt was always to identify the requirement, develop a thread of the requirement development, so you get to how you're going to verify that you're meeting the requirements through test. And we used to keep track of it for those of you who've been doing traditional systems engineering, you're familiar with a tool called DOORS, which was nothing more than a big spreadsheet that just related a set of requirements to a set of verification testing. And what MBSE brings to the table now is that you're able to develop that test planning and the test relationships much sooner. And there's another concept called capability-based testing, which is intended to identify what is it that I want my weapon system to do later and develop tests based on the system model now that will demonstrate that I'm either achieving those requirements or not from a capability base, rather than just verifying that something meets a spec. So yeah, it's a lot different now. It's a lot more involved.
Yeah, so go ahead, Rhett.
Yeah, I'd like to expand on that a little bit. What Rich said with like a capability, for example, you can tie said capability to all the functions your system needs to perform for that capability. Then you can pull in the requirements and their associated verification methods, and you can do all this semi-autonomously. Then you can assign those to, say, testing vignettes, or something like that, and then auto-generate like test run matrices and other things like that, all of it based on the same data. That's an important piece here, is instead of it being tied in different artifacts, so you have one in your CDD and one in your system spec and so on and so forth, it's all that same data in the same place. You're creating queries against that data and using that to generate your test run matrices and so on. And these are in the context of those things that are important to that test. So it's not just to look at one singular requirement or set of requirements together. It's to look at those requirements together with their interfaces, the scenario in which they're used, the conditions in which they're used, the functions that they're attached to or assigned with, and in the context of the capability that they're in development with. It also lets you do some interesting things like begin to identify the testing equipment you're going to need, the testing process earlier on, and where you'll use that equipment in those test pieces.
Yeah.
So
it sounds like we're getting more information earlier, we're getting better information, and like you just said, it clarifies the type of resources that you'll need once you figure out what that solution is. Awesome. So let's, I think you answered my second question, which is how is MBSE different from traditional systems engineering? So let's move on to, in the first episode, Rich, you gave a great example of how system engineering could be applied to like building a house. Is there another example that can kind of give a picture of what MBSE is in that sense?
Sure, you can. When we one of the examples that we use when we're teaching what MBSE is going to do for you, we use the example of an automobile, and we talk about establishing a set of requirements, and we could walk through the 4 pillars that Keith mentioned earlier, and you could look at if I want a car, talk about a simple requirement. I want a car to stop from 60 to 0 without skidding in, say, 20 seconds or 10 seconds or whatever it is. And that would go into the requirements pillar of the model. You would talk about the physical description of the structure of the model by looking at all the physical components that are involved in making the car do that. Wheels, tires, brakes, anti-skid control, all of those elements, even down to the operator's foot on a pedal somewhere to make the car stop. And that would be the behavioral elements, the structural elements. Then you would talk about the behavior and how those things interact when you put your foot on the pedal to stop the car, and how the anti-skid system will come into play to keep it from going into a skid. And then you would go into the parametric discussion, which is where the model will do the analysis to say how fast will the car stop given the structural design that you've come up with so far and its performance. So yeah, you could do it with a car, or you do it with an airplane, or whatever kind of system you want. You can, I don't know how you could do it on a house as well, but the point is that you generally describe whatever it is that you're trying to do in terms of its requirements, its structure, its behavior, and how it's going to play together.
I'd add
I would also add, Ian, I loved what you said about how this brings a lot of information into play earlier, because what the real primary benefit of MBSE is learning and understanding your weapons system earlier and identifying risk earlier. And all the big savings that come from MBSE are the result of bringing risk understanding to the program earlier.
So one of the things that people say is we move knowledge to the left. As we develop a system, we're moving the knowledge of that system further left when it is better utilized in decision making for the future of the weapon system, to make sure it meets the user's requirements, and certainly has all of the logistics and product support aspects built into it as well. So you're moving that knowledge more left.
So one of the other values associated with model-based systems engineering is reuse, right? So you've got a area of polymorphism, as we used to talk about it in the software development world, is that when you build an object, you can reuse it, right? So using the analogy that Rich used on a car, so if the brake system was common on several different cars, you could reuse that part of that model, all right? And you just change the requirements going into that model, may change some of the behavior associated with that model. So that's the area of concordance and polymorphism. Also, the value associated with model-based system engineering is you can work collaboratively on design with different parts of the system at a moment's notice. So we go to an allocated baseline where I'm allocated size, weight, power in an aircraft. Each section goes off and does their little thing, and then they come back and says, I didn't have enough space that was allocated to me, so I'm going to go and actually start pushing the design envelope down to a more highly technical or technical risk area to get the design down, where if I would have been able to collaborate with, say, propulsion or for aircraft structures, I may have gotten that value back of size, weight, and power, so I wouldn't have to go down that road of technical immaturity. That way it allows me to get the design through a lot quicker. So that speeds up the process, because now we're actually understanding our trade space on a moment's notice instead of every 6 months to a year where we all get together and talk about it.
Right.
I'd like to add some of the power of the MBSC tools is they allow you to do a lot of those execution or parametric execution directly in the model, or tying it to an external tool suite. So if you have in the swap example, you can compare your allocation to how much you're using, and then surrender that remainder back in near real time, either directly in that model or tying in a different tool and using that tool to link that data. And in addition to that, you can compare those to your requirements in semi-real time as well.
Yeah, so talking about what Rhett just brought up is allows you to use the model as a decision-making tool instead of using biases that come out of who gets to your desk first, right? So
Yeah, so it sounds like there's a lot of automation that happens that probably takes a lot of time out of, and I think you have all said this, that takes a lot of time out of what was the process before. So you also hit on the fact that it brings a certainty to the designs that are happening and better decision making. Where do I want to go next? Let's look into the future now, I guess. How do you see MBSE evolving, growing? Where is it going in the future?
well, an area where I see where its value would be is if I was to, let's say the helicopter replacement program, if we was to model the functions and behavior of the current H1, Y, and Z, right? Then when you replace that aircraft because you have more capability than the current aircraft has available to it, you can use those behaviors or that operational functionality and roll that into the baseline requirements for the next aircraft instead of redoing it all from scratch. Right. So I think there's value in that. Also, feeding back into the test. Once you get into test and you actually validate the system and the issues associated with that, feed that back into the requirement set once again to now provide information on how to better design later on. And then thirdly, I see where now we actually have models of the entire system. And as the system gets upgraded, either be an ECPs or pre-programmed improvements, those capabilities are actually rolled into the model, which feeds into the JSIDS process, which right now the JSIDS process stops at the CPD, where they only have a small subset of the total functionality of the system at the JROC.
There's another thing that, and I know Keith is very familiar with this, is the system of systems aspects of once you get models, a digital representation, if you will, of the behaviors and functions and requirements of a system, you can start linking a system with another system as represented by that model, and you can start doing system of systems analysis, system of systems work, decision making, and all that kind of stuff.
Absolutely.
So you wanted to know where it's going and where it's been. I think a lot of things have converged to make model-based systems engineering feasible in the first place, and that the power of computing has grown. The development of a language to do model-based systems engineering in, the common one is a thing called SysML, which is a common language that people can define requirements and all these elements of the model that we've been talking about in a way that's commonly understood and brought together. You're also starting to see many companies starting to use it and try to implement it. So a lot of the OEMs are doing it. The Navy is taking the lead, especially in aviation, to develop model-based systems engineering as a path to the future. I've got to tell you that I came to AVIAN because AVIAN is directly involved in supporting the Navy and developing the processes and means of implementing MBSE. And so where it's going from here is that everybody's trying to figure out how to put it together. And we have the opportunity at AVIAN to help the Navy do this. All of us are involved in supporting specific programs to do it one at a time. We're also involved in supporting the system engineering team at NavAir. Their sole purpose is the transition from document-based systems engineering to model-based systems engineering. NavAir is trying to develop an entire digital environment to not only address the system model and systems engineering that's the focus of our conversation today, but to bring in other elements like sustainment through PLM and attaching the PLM inputs coming out of the system model instead of just doing it later, which is typically how sustainment is developed in programs as an afterthought. We're looking at the integration of the system model outputs into what the capability-based test tools are doing to predict the performance of aircraft based on the model output. So there's a lot of exciting things coming together now, and we're at the apex of bringing that stuff together. And it's one of the areas where AVIAN is developing its strengths in terms of having a lab that's been put together to do some work to start looking at integration of these tools. We are training modelers, which I am not. I'm not a modeler. I'm a systems engineer. Rhett is a modeler. He knows how to do that. But the development of an integrated team of systems engineers with modelers, because the systems engineers still have the vision of the architecture of the weapon system they're trying to develop, and the modelers bring all that together. And you need an integrated team of folks to do that, along with all the competency engineers and other specialty engineers and testers and logisticians to bring a program together. So the future is coming like a freight train. It's moving very fast. NAVAIR is really working hard to try to get everybody on a similar path so that it's not just all haphazard. And we have the opportunity here to help them do that. And the future, I think, is bright. Systems engineering is undergoing a renaissance as far as I'm concerned with all this. And we're going to be able to do much more in the future. I get excited. I'm sorry.
I think to add on to what Rich said, it's pulling some of those things together, like test, like some of the other disciplines, but it's that integration together is the important part. It's not enough to just model, you also have to architect. Architecting is pulling together all these disparate disciplines and making them work together in one system specification, in one centralized location where the OEM, the government, and all those specialty or other competencies can work together. So not only are we working to pull those in and enable that for everyone, but we're working to get the people trained and knowledgeable in that beyond their typical day-to-day methodology. So whereas you'd normally do it in Excel, an architect or modeler will enable that for you in the model and help you get there. So it's not enough to just take a model and then have the modelers working in that model. You need to bring in everyone together and have that single source of truth. If you're bringing in Excel sheets and you're bringing in Word docs and using those to generate your model, you don't have a single source of truth. You have layers of I don't know if confusion's the right word, but layers of interpretation issues between the primary source and the model or the representation of your system. So it's the job of architects and modelers to work with those SMEs, work with those systems engineers and model-based system engineers to bring in that data, to bring in that user community, to bring in those specialty domains. I think that's where we're going next, is pulling all those together and enabling each individual from their own competency or their own capability to work directly within that model.
Yeah, and I'm going to say something. Hopefully, I don't offend anybody because I really respect all the work that you guys do. But it seems like it's this merriment of old school and new school, where systems engineering is that old school and overarching category, and model-based systems engineering is that new school take on what I'm calling old school systems engineering. So really cool to see that AVIAN has this team and is building this team of both folks who have been, like Jim mentioned when he introduced himself, been in the business for 35 years, and then Rhett, who is a modeler and learning all these new techniques. Let's wrap it up. We're almost to 30 minutes. Any last minute kind of AVIAN plug? So we talked about the SE bootcamp a little bit that we stand up. We talked a little bit about some other capabilities. What other capabilities do you guys want to hit on that we offer from AVIAN?
I'd like to focus on consistency. A lot of people can create a model. How useful is that model is a very, very separate question. If you put a bunch of stuff together and you throw it in a containment tree, you now have a bunch of stuff in a containment tree. unless it is aligned to a schema, unless it is set up in a very methodical and consistent way, it is unusable. So that sets a lot of models apart from each other. Is that data organized in a way that you can query it, that you can chain it, that you can integrate it with other things, and that those things are usable for the people that need to bring in that data, those external SMEs. So I think that's something AVIAN does very differently from a lot of companies. And it's hard work. You have to create that format, you have to work with those individuals and bring it in. And the format will look different. Sometimes the process will be a bit different. That's another point where we excel. It's not just creating that specific format and that specific consistency in that schema. It's creating the process and the validation rules and the guidance and style guides and so on to enable that for everyone. So you have people who are modelers, you have an architect who designs this, but they by themselves are not enough. You need to bring in all of the SMEs, the subject matter experts from all of their areas to enable to fill this in a usable and complete comprehensive way. That's where I think the power of modeling is enabled, and I think AVIAN does that well.
Well, I think one of the values that we get out of from AVIAN is like myself and Jim have been around, and also Rich been around systems engineering for 30 plus years, right? So we have all this sage of knowledge, but we have we have a breadth of knowledge, but not a depth in model-based systems engineering. So we rely on folks like Rhett within the company to help balance all that out between our breadth of knowledge associated with systems engineering, but pulling in that depth by using Rhett and some of the other folks at AVIAN that actually understand at the detailed level what MBSE is and how to invoke it, so we can provide that value to our customers at the sage level and also at the depth level associated with model-based systems engineering.
I think one of the things that kind of ties a little bit about what Keith said and what Rich has been saying is I think we're helping out, AVIAN's helping out a lot in the defining the art of the possible. Keith mentioned we have a lot of experience with systems engineering. So we know what kind of information is required, what kind of decisions are being made, what kind of issues that are being faced with systems engineers. And we have people like Rhett that bring the power of model-based systems engineering and some other people within AVIAN. And to sort of bring those two together, how can we model something to help potential issues or help potential decision making that needs to be done when a program, as a program develops. So we're spending some time, I believe, helping out that and defining that art of the possible.
Yeah, and Rhett mentioned the importance of integration of capabilities, and one of the things that we're really paying close attention to is the customer has long struggled with integrating a team of engineering and testers together. And Jim's background is frankly a lot more in test than in systems engineering. And what we're trying to do here is help NAVAIR bridge that gap. When they talk about capability-based test, they're talking about bringing the test discussion way forward into the development and design process and ensure that we demonstrate capabilities earlier and reduce risk in programs. So again, it's all about bringing knowledge to the left and better understanding where we're going. And we get that, and we're trying to build those bridges where they didn't traditionally exist. Similarly with the sustainment side and what PLM programs have tried to do in the past.
Awesome. All right, so I think we are good to wrap it up here. Thank you guys for joining me today. On the next episode, we are talking about what it takes to be a modeler. So we gave this overview of what MBSE is. In the next episode, we'll dive deep into I'm imagining, the education it takes and probably some of the languages you need to learn and things like that. So thank you guys again for joining me, and I will see everybody next time.
Okay, thank you.
The Model Vision podcast is brought to you by AVIAN. At AVIAN, we provide extraordinary support in the areas of model-based systems engineering. We help our customers detect problems early using modeling with a purpose. With AVIAN's MBSE network, we provide a collaborative ecosystem to access, define, and implement a tailored MBSE approach for program success. AVIAN's model-based systems engineers work with SysMill using Cameo software to replace the document-centric nature of typical systems engineering. Our engineers expose vulnerabilities within your system before implementation, ensure speed to the fleet with a solution that brings clarity early, enhances the chief engineer's capabilities, creates a holistic view allowing for better decision-making, and simplifies complexity. Everything works together to bring certainty to your design. If you're interested in learning more about AVIAN's capabilities within MBSC, you can visit avian.com/capabilities.